Um, make sure, I would suggest early on with this one, because there's going to be some vocabulary that you're not familiar with. Make sure early on that you take note of what all the different vocab words are. Like if that means looking up in the appendix of the glossary section of your textbook, or online, or using an AI to help you talk it through, that's great. But have some working definitions. It'll help you to understand what's going on as we go through things. Because some of these are kind of maybe not familiar words for your everyday language. We'll talk a little bit about like just basic wave behavior. So again, some words that may or may not have come up in math class. When I measure this distance here, this is a wave, or I measure this distance here, I'll label them both A, because both of these guys are what we call the amplitude. So it's all well and good to have a vocabulary list, especially if you're an English language learner, but I would say for everybody, it's also nice to have a visual, right? So this is what an amplitude is. When we talk about a wave, we also will talk about there being a peak or a crest. You may encounter friends, websites, YouTube channels that, and I'll just throw it up above because I'm not going to use it as one of my main words, but they might just use the word maximum. I'm going to use the word peaks and crests primarily. When it's at its low point, of course, those same people would call it a minimum, but I would call it a trough. Okay, a trough is a low point. And I believe our textbook does too. Okay, so that's why I'm kind of leaning that way with the language. But the maximum points and the minimum points on a wave, a trough, TROUGH, if you're working on the spelling there. Nope, just a trough. Right. So we got a peak and a trough. Now, this wave looks like it's just a snapshot. And this is the problem with paper, is that it's not animated. Because this is actually a picture of a wave that's traveling. It's a traveling wave. It's actually what it's called, but it has a velocity. And that velocity indicates that waves have a direction of travel. Okay, so this wave, like any other wave, has a direction in which it's traveling, a velocity vector. There's also this dotted line here. And waves need, well, classical mechanical wave needs a medium. And so we talk about that medium, like for example, water has a resting position. If we're talking about sound waves, we might talk about its baseline particle density. But let's just stick with water waves for a minute. The resting position of the medium. And then here's another one that people have probably heard a bunch of before, and it's wavelength. I think the wavelength has a name that's pretty much self-explanatory. A wavelength is the length of a wave. There you have it. Okay? There's a fancy definition. But in terms of the variables that we use, and we'll work towards math at some point here, I just want to introduce the idea of this variable right now. We use the Greek letter lambda. The Greek letter lambda usually is written something like this. Every font is maybe a little bit different, but it looks a little bit like a weird Y upside down or something like this. It actually is no two alphabets are the same, but it's almost like the Greek equivalent for L for length, lambda, right? In my mind, it also kind of looks a little bit like a cresting wave, but whatever. This is the Greek letter lambda. As the variable. Okay, so just introducing that Greek letter right now. And we use use Greek letters a lot. Alpha, beta, gamma. You guys have a question about it? No, it's good. All right. Yeah. Like a lambda. Lambda. Yeah. Lambda. But it's like I don't know, the letter T in English. When do you ever write the word T, right? It's actually spelt like that. But unless you're a Scrabble person, who cares, right? So lambda. We just usually write the letter. You're never going to have to write the name of lambda again, okay? Just like, hey, maybe you didn't even know that's how you spell the word T. I don't know. Yeah, why would you care, right? Anyway, except when you're playing Scrabble and you got to have a really dense letter grid. Anyway, yeah. So transverse waves. This is a whole thing. It's a medium when a medium is disturbed in a specific way, though, so that the particles. Now, this is going to seem like a little bit a weird thing to say as I write it until I make sense of it. So that the particles move perpendicular to the direction of wave travel. Now, I'm going to rely on springs, and it seems strange that I'm going to rely on springs. Now, if you're watching the video because you're sick today or something like that, you're not in class, you're not going to see the demo later on, but I'm going to use like this spring that looks like this, okay? So it's a great big spring. So just like to give you this idea of what I mean by a spring, like the scale of this thing. This thing is like, there's a lot of spring here, okay? And, as I hold it up, people in the class, you guys can see this is like a 2-meter long spring, right? This is it's a spring, like from the spring store. I bought it after winter last year. I believe it was spring. Anyway, did you just shake your head at me? Yeah, I deserve that. All right. Anyway, I want to draw a dotted line. That's what I want to do. And actually, because maybe I need to plan this a little bit. When you're sketching something, you got to plan things out. So I'm going to give myself like really light sketch. And what I'm trying to do is sketch out a sinusoidal curve. Like a sine function. And the reason I want to do that is that I believe that giant spring I just showed you, see this here? This is my little hand. I'm going to draw it like a little mitten. That's my little hand. And I believe that if I take my hand, and we'll do this as a demo later, and I hold on to the end of a spring, but I wiggle my hand up and down. Okay, like raise it up and lower it like this while I'm holding on to a spring. What I believe would happen, and we'll do this, we'll play around with springs, is the spring, here's the coils of the spring, will wiggle around too. In fact, I should be able to do this so that I can make the spring do this kind of like wavy action. And if you were a kid that played with skipping ropes as a kid, I bet you did this when you were a child. Oh, don't worry about that. I bet you did this when you were a child. If you lay the skipping rope down on the ground, can you imagine wiggling it back and forth? I distinctly remember we used to play this game called Sneaky Snake or Snaky Snake or something like that. There was a song associated with it. I don't remember the song anymore because that was years ago. But we used to have to dance back and forth over the snake, and the person that was wiggling it back and forth would wiggle it faster and faster as you dance back and forth. And eventually the snake would hit your foot, and you'd say you got bit by the snake, and then you were out, So this idea of the snaky snake on the ground is something that I have experience with, and maybe some of you do, based on the little knowing smiles. How many people played something like Snaky Snake when they were a kid? All right, so a quarter of the class. And those of you that didn't, maybe you should. I don't know. Sounds like fun. All right, so we got this snaky snake kind of spring thing that's going back and forth. And what I said in writing was, The medium is disturbed so that the particles move perpendicular to the direction of wave travel. Would you believe that as I'm wiggling this spring, it would actually send wave crests traveling that way, away from my hand? That makes sense, that there would be a wave velocity traveling away from my hand like this. But it says that there are perpendicular motion of the particles at any given moment. Can you imagine that the particles would go in this direction? When I say particle, I'm thinking about like the coils on my spring. That's actually one of the reasons why springs get used, because you can imagine a coil going up and down, right? The coils on the spring are going to wiggle up and down. They don't actually travel to the right. The coils stay where they are. And if you really wanted to emphasize this with a skipping rope, you could tie like a little piece of pink string in one spot on your skipping rope, and what you'd be able to see is that the pink string just wiggles back and forth, whereas the skipping rope looks like it has a wave traveling along it. You guys picture that with a skipping rope? Like, skipping rope's a good model for this too. Anyway, if I was going to think about other properties, this is called a transverse wave. If I was going to talk about other properties of this wave, one property might be to talk about the wavelength. And so if I were to take 2 points, like these 2 points here, I could measure the distance between these 2 points, and the distance between those 2 points is the wavelength. Lambda. Oh, I said this out loud, but let's label it motion of the source. I got a wave source here. In this case, it would be my hand wiggling things back and forth. People say, oh, are other particles going up and down? Sure, there's another particle over here that's going down. Why not? Right? All right. So there's this other kind of wave called a longitudinal wave. And I'd be willing to bet that everybody thinks of a transverse wave when they think of a wave. That's probably what you think of. You probably don't think about a longitudinal wave, but it is a wave. It fits the definition. So it's a medium that's disturbed so that the particles move back and forth along the axis of travel. What do I mean by that? All right, so I'm going to draw myself another dotted line just to help out with the drawing of this thing. And I'm going to draw myself another hand that looks kind of like a mitten. Okay, I'm trying to keep this low in terms of the artistic demands. Okay, so we got a little mitten here. And again, we'll draw in the arrows for what this hand is going to do. This hand is going to go back and forth from left to right. So instead of up and down, it's going left to right. And you can imagine if you did this with a spring, what that would mean is that sometimes you're punching forward on the spring and sometimes you're pulling back on the spring. What that's going to create in terms of a spring pattern is that, here, maybe I'll put some dots that are equally spaced out here just to help me. And you can do this too to help you with your artistry. Okay, I'm going to equally space out a few dots. And that means that sometimes the spring will bunch up. And sometimes it will space out. Sometimes it will bunch up. Sometimes it will space out. See what I mean? If I take my hand, I hold on to a spring, just like this actual spring here, and I push it back and forth, sometimes it'll bunch up and sometimes it'll spread out. Follow? Now, there's names to the bunching up. We don't just call it bunching up and spreading out. We call the spreading out portions rarefaction. Rarefaction, not refraction. Refraction is when a wave changes direction because of a change in speed. Rarefaction means that there's less stuff there. And so we could talk about old-timey words like to become rarefied. It means there's less stuff there. If we talk about something that is rare, there's not much of it, right? Gold is rare. So that's rarefaction. That's decreasing of the density. The bunching up regions, this is a more familiar word for us, is called a compression region. Just because the particles are compressed together. The coils are compressed together. So compressions and rarefactions. And that's my quick definition of that, a visual definition. And I really do think visual definitions are helpful. But add to your terms list. Make sure that you know what all these terms mean. Now, having said that, that does not look very much like a wave to me. That looks like a bunch of compressions and rarefactions. But what I also notice is if it's a density thing that I'm looking at here, can you imagine that, here, I'll turn my page sideways for a minute. If I had a graph like this one, and I wrote on the vertical, oops, oh man, I need a whiteout, really? If I wrote on the vertical axis of my tiny little graph the word density, and I don't want to be very official or formal about this, I'm just going to say if that vertical axis was density, I could say, all right, so the baseline, that's if I didn't touch the spring at all, just standard compression. It's just sitting there. But when I push on the spring, the density gets higher. And then when I start to pull back again, the density gets lower until I pull fully back, the density becomes really low. And then I push forward again. And then I pull back again. You know, and I could keep on going. I know that I exceeded the x-axis on that one. That's okay. But what I'm saying is that I could graph the density. And the fact that I could graph this visual, and when I graph it, it is a wave, tells me that that visual there, that spring, when I'm doing this longitudinal motion to it, it has wave properties. Okay? There actually would be a spatial distance between there and there, and I would call that lambda. But you know, when we're measuring lambda, that looks like an x, it's a lambda. When I'm measuring lambda, really the definition of lambda isn't between the points where it crosses an axis or anything. The definition of lambda is the distance between two identical points. That's the real definition of a wavelength, the distance between two identical points. So look, couldn't I have just chosen the peaks? It would have fit onto my diagram better. If I chose the peaks, aren't those two identical points? So really, that's also lambda. Now, I am not a perfect artist, not by any stretch of the imagination. But you know, if I were to come along and measure, if I was a good artist, and I did this perfectly, see how that's 3 centimeters? Oh, I didn't do too bad. The distance between the peaks is 3 centimeters, and the distance between the x-intercepts is also about 3 centimeters. I didn't do so bad. Those are both lambda, okay? I could choose any 2 other points that are identical. Look, that guy there, I'll put an X on it. Don't do it, though. Don't mess up your picture. I'll put an X there. If I measure from X to X, see how it's also 3 centimeters? It's all good. 2 identical points. That's really the definition of a lambda, the difference or distance between those 2 identical points. I want to pause there for a minute because this is all very wordy.